Okay. The aim of this work is to investigate on the microstructure and the geometric distortion, residual stresses, and fracture behavior, and to find FEM workflow using numeric simulation analysis to find the optimized process parameter to reduce the waste and improve the sustainability of the additive production. First of all, let's introduce the shift memory alloys. They are a type of alloy that can recover entirely or partially the deformation. And among the shift memory alloy, we will see an alloy that presents the one-way shift memory alloy effect. This effect is caused by the lattice structure that really is the form pass from twinned martensite to the twinned martensite, and the shift memory effect is activated through the heat up of the lattice that go to austenite phase, and after the cool down to the twinned martensite again. This type of alloy have many innovation applications like medical or aerospace, such as deployable structure or cardiovascular stent. The production of this alloy is use LPBF technology that use focused laser to build layer by layer an object. The sustainability challenges of LPBF technology are the high energy consumption and the elevated cost of feedstock and the risk of defect. In fact, it's important to find a way to reduce the waste, and in a way it will be possible to increase the sustainability of the technology. The typical issues of products of LPBF are the development of residual stresses and the formation of non-equilibrium microstructure with a lot of defect like porosity, cracks, wrapping, so on. So the solution is to find the optimal choice of parameters. The raw material that we use is iron shift memory alloy. The composition is with 30% manganese and 5% silicon. And the sample that we built are some small plate with 10 per 10 per 3 millimeters of dimension and a lateral fillet of 0.5 millimeters. This alloy is an iron shift memory alloy that typically present three microstructural phases, such as austenite phases, martensitic, and epsilon martensitic and alpha prime martensitic. It's different from the more expensive shift memory alloys such as nitinol, because it has a limited elasticity, but it's also more thermal stability. And the one that we use also a limited oxidation endurance due to the absence of elements as chromium. The technology that we use for the print is a machine from Prima Additive, and the parameters are shown in the table, and we use high volumetric energy density of 139. And also the printing strategy is shown in the on the right. We see the specimen were printed using a strategy that consists in doing before a contouring, and after the infill doing with a strategy of stripes with a filled height of 4 millimeters and an overlap of 0.1 millimeters. And also for the production, the angle with the recorder direction was chosen to 15 degrees to avoiding collision. And so for the numeric simulation part, we use a workflow that follow the realization of a KAD model, and after the realization of the material model based on experimental results and literature for similar alloys, and after we use the ANSYS modules for additive manufacturing that allow to set the process parameters on for the simulation, and it calculates the thermal result before, and from the thermal result of the production, it will calculate the mechanical results such as deformation, residual stresses, and strain. And for this, and after, okay, and well, for the printed parts characterization, it's used also the optical microscopy for microstructure analysis, SEM for analysis of feedstock, and the fracture surface analysis, and EDS and XRD for the analysis of the feedstock, and also stereo microscopy for the geometrical analysis of the printed part to confront with the FEM results. Firstly, the feedstock analysis can show the that the feedstock is composed by mainly spherical particles without a lot of defect, except for some satellite particles, as shown in the red circles. The dimension of the particles are slightly smaller than the range that were specified by the supplier, but the packing density were generally good, and we also observed the absence of contamination. And also the other sample of feedstock were taken after the print. A sample A was taken from the build plate powder, and a sample B was taken by the powder that was blown away from the protection gas. So there's some also sputters and more defects, as shown in the picture on the right, and less spherically geometry than the other powders. And from the ADS and XRD analysis, we can see that the composition after the print changed only slightly, and for this sample A, for the sample B, the iron content is a bit reduced. And also from XRD, you can see the presence of gamma austenite phases, and all these data can indicate that all the powders are suitable for the sieving and recycling process that allow the increase of sustainability of the process. And also from the FEM results and the confront with the geometry analysis of the printed part, we can see that from the analysis of the top, we see that the results are similar from the simulation to the real results. And also we have reduced thermal cycling effect due to the optimized scanner strategy, but we also observe edge wrapping typical from such type of components of additive. Well, for the lateral results, we can see that the FEM results underestimate the deformation of the body. So for a value to up to 100 micrometers, and also we observe the increase of ruggedness, and that maybe it's caused by the greater, the suboptimal laser effects with the body. From the residual stresses results of the FEM, we can see that the stresses are focused on the center and on the top surface of the sample. And also from the crush section, we can see that the stresses are focused on the center and on the edges of the sample. And in many areas, we have the residual stresses is the ultimate stress, and this is, we can see from optical microscope results that we can observe several cracks indicated by the red arrows that are caused by the residual stresses during the printing process. And also we can see the several cracks that goes from the edge toward the center, passing through the many defects that we can observe, such as porosity. From the microstructural characterization, we can see several defects, such as porosity, like K-hole porosity and unmelted particles, and also gas porosity. Indeed, we can observe an high porosity of the body that reduces the density up to 98% of density, and also we can observe several cracks that propagate through the melt pulse structure of the sample. From the results of fractography analysis, we can see that mainly we can observe a brittle fracture behavior from caused by the many defects of the sample, and we also observe minor areas of ductile fracture, as we can see indicated by the white arrows that indicate the small dimples area where the fracture is ductile. And from these results, we can see that the mixed mode fracture, the fracture mode is mixed, but it's mainly brittle, and the defect acts as a crack initiation sites that leading to transgranular fracture, and some small dimples at magnification indicate the presence of ductile region where there is the less defect than the other areas. In conclusion, we can say that the simulation, the ANSYS simulation is can provide compliant results as the printed parts, and but there are some limitations due to the impossibility of fully calculate all the influence of the process parameters. And those, but also we can say that from the FEM simulation, we can prevent the defect before printing, because the results are similar to the printed parts, so it can be used as a tool to increase the sustainability of the process. Also, from the you observe the influence of process parameters and printing strategy that may cause several defects due to the high volumetric energy density. And also we observe the mechanism for the mixed fracture behavior of the iron, manganese, silicon additive manufactured parts that is caused by the process inducted defect. For further investigation, a more deeper analysis of process parameter, and also the investigation heat treatments it's recommended for future work. Thank you all for the attention.